Hello, welcome back. The title of this lesson is called Average Velocity and Average Speed, and this is part 1. So in this lesson, we're going to introduce the concept. We'll draw lots of pictures so you fully understand what average velocity looks like in terms of a chart or a graph, also how to calculate it and how do we interpret it. Now we all have an idea of what velocity is, right? Velocity, if you just think about the units, meters per second. That means how far do you go in distance, meters, compared to or divided by how many seconds it takes. So the units of meters divided by or per seconds, that basically tells you what the equation has to be for the idea of velocity. But in this case, we're talking about only the average velocity. So the place where we're going is we want to eventually understand the concept of instantaneous velocity at an exact moment in time, right? When you're driving down the road, you can be speeding up or slowing down, and at every moment of time, you do have an instantaneous speed at that moment, right? But in this lesson, we have to first talk about the average speed taken over some time interval, or the average velocity taken over the time interval, and then we'll talk about the difference between that and also the average speed. There is a little subtle difference there, and we have to understand it. All right, so before we go any further, let's talk about what the average velocity, how do we calculate it? And what we'll do is we'll draw a lot of pictures. We'll do a little calculations on these pictures here, right? So what you say here is you can write V with a bar over it, and the bar means average. This is not a vector symbol, even though velocity is a vector. This is just a bar, and it means average. In some books, you might also see it as V with a little AVG underneath here. So these things mean the same thing, and this is just the average velocity. Now, in shorthand notation, we say that it's equal to delta x. That means the change in the x position, how far it moved, the distance, divided by the change in the time that's elapsed. So these triangles, remember, they mean change. So it means change in the position divided by change in the time, right? Now, we already learned in the last lesson what delta x is. That's the displacement. It's the final position minus the initial position. That's what delta x is. It's the subtraction of the two positions divided by, here we have the change in the time. So it's the final time minus the initial time, right? So what we have here, don't forget, is motion only in one dimension. So right now we're confining ourselves. Imagine a piece of string pulled tight here, and there's a bead on this string. It can only go back and forth on this string. We're only considering it to be one-dimensional motion along one direction, one axis, the x direction, right? In the future, we'll open it up to two-dimensional motion. We can throw a baseball, and then later three-dimensional motion as well. So this is something you need to remember. It's not something that's so hard to remember. You already know that this has to be the equation for the average velocity because this is the units of here would be distance in meters, and the unit of this would be time. So you would get meters on the second and on the top and seconds on the bottom, meters per second. All right. Now the other thing I want to say is that when we talk about the average velocity, so what's really going on here is in real life, when things move, they can sometimes be maybe speeding up if you're accelerating in a car, and maybe sometimes you're slowing down if you're braking in a car. So at every moment of time, the velocity is changing. But when we calculate the average velocity, we're only looking at 2 points along the path, the initial and the final. And we're ignoring the speeding up and the slowing down that's happening, and we're only interested in the average across that span of distance and time, the endpoints, in other words. So the average kind of throws away the intricacies of the motion in between, and it just calculates the average, which is just the sum total of how far it traveled and divided by the time, right? That's an average. Later on, in the next couple of lessons, when we talk about the instantaneous velocity, what we'll do is we'll make that window shorter and shorter and shorter, the distance and the time window, until we end up with an instantaneous velocity at an exact moment in time. But for now, we have separated distance and time to calculate this average right here. So the easiest way to proceed is to try to apply this thing to several different situations and understand it. Now, it is motion along the x direction, which we drew in the previous lesson along a kind of a number line that was horizontal. But in order to understand more about what's going on, we're going to turn that on its side. And what we're going to do is we're going to draw the x-axis, instead of horizontal, we're going to draw it vertical like this, right? And what I'll do is I'll draw a horizontal axis as well. And you might say, well, wait a minute, you just said it was one-dimensional motion. Now you're drawing 2 dimensions. This dimension is not distance, this is time. Now you have to get used to seeing something like this. Every moment of time that ticks on in 1 second, 2 seconds, 3 seconds, 4 seconds, that's what this is. This is telling me, basically if you turn your head sideways, this is the number line, the 0, this is the positive x values, and here's the negative x values. So you take that number line from the last lesson, you turn it on its side, that's what we have right here. All right, so let's say up here we have, here's 1, here's 2, down here we have -1, and here we have -2. So let's take the situation where we have the following graph, and let's see if we can figure out what it means. What if I have a graph that looks something like this? It's completely flat like this. Now, before we do any calculations, can you tell me, now notice my line's not perfect. You see how my axis was not perfect, so it's kind of creeping up. You have to imagine completely flat lines here. What does this look like in terms of the motion? When you see a flat line like this on a position time graph, what it means is that the object is not moving at all. It appears like it's moving because you see the line here, but don't forget, when you go this direction, it's the time. So what it's saying is, after 1 second has elapsed, then you're at a position of -1 meters to the left of the origin. Because remember, you put your head sideways, these negative numbers are to the left of the origin, and the right, the numbers up here are to the right. You got to flip this over horizontal to get to our horizontal number line. After 1 second, it's at this position. After 2 seconds, it's still 1 meter to the left of the origin. After 3 seconds, it's still 1 meter to the left of the origin. And every second that goes on forever, it's still in the same position because this is the position information. No matter what time you are, even before the experiment began, when time is negative, you're still in the same place. So this is a situation where no motion happens at all. So I'll just put this right here, no motion. Now, because we know there's no motion here, we expect that if we were to calculate the average velocity between any 2 points in time, what should we get? We should get 0, because we know the thing is not moving. Let's apply it and see what we get. So what we do is we say, all right, let's go over here and calculate the average velocity. We'll write it with a little bar on top, and we're going to say, okay, x2 minus x sub 1 divided by t2 minus t sub 1. All right, so I have to pick 2 points on this line, right? And it doesn't actually matter because we're going to get the same number no matter what 2 points in time we pick. So let's pick, you can mark this if you want to, but let's just pick these 2 points in time. The final position, like it's moving this direction, or I should say time is moving this direction. So here's the final point in time. The position is -1, so that's the first position. X is equal to -1. The initial position over here, the position was still at -1, so we subtract -1. You see you have a -1 minus a -1 because the position never changed. Final minus initial was -1 minus a -1. Now on the bottom, let's just say that this was like 3 seconds here and this is like 1 second here. It doesn't really matter. T2 could be 3 and a 1 second would be the initial. So initial and final, right? Between these 2 points in time, the thing did not move. What do we get on the top? We get -1 plus 1, and on the bottom we get 2. And what do we get over here? We get a 0 on the top and a 2 on the bottom, so 0 meters per second. And this is exactly what we expect. The thing shouldn't move. Now what happens if we pick a different 2 points in time? Let's pick, I don't know, these 2 points in time over here. Well, the final position is still at -1. The initial position here in x is still -1. So the numerator is the same. The bottom might be different points in time, maybe 7 seconds minus 5 seconds, let's say, but the numerator is still going to be 0. So when the position doesn't change, no matter what 2 points in time you pick, you're always going to get a change in position of 0, a displacement of 0. So the velocity, the average velocity is 0. All right, so there's no movement here. We predicted that that would be the case, and the average velocity we got is 0, and we just did a thought experiment where we convince ourselves that the average velocity, no matter where you look here, is just 0 meters per second. Now, I want you to file something away in the back of your mind. Remember back from algebra or calculus if you're taking calculus. What is the slope of this line? Remember, horizontal lines is rise over run, right? The slope of any line is rise over run. Well, this line is not rising at all. The rise is 0. So if you calculate the slope of any horizontal line, you get 0. Notice that the velocity was 0 and the slope of this line is 0. What we're going to find is that when we have a position time graph like this, the slope of the line that you have governs or tells you what the velocity is. The slope of the line on a position graph, or the slope of the position graph, is the velocity. That's very, very important. The slope of this line was 0 and the velocity was also 0. Why? Because rise over run, right? But rise is how far the thing goes up. Notice x is in the up direction. That's rise on the top. And run is the time dimension over here. So what we've calculated here, even though I put it as delta x over delta t, really all we calculated was the rise of this graph on the top and the run on the bottom, rise over run. We calculated the slope. So the slope of a position graph, the slope of the line that you draw on a position time graph, is the velocity. And that's something fundamental to calculus that we learn in calculus, that we call it the derivative of the position is equal to the velocity, which just means the slope of the position graph is equal to the velocity, and we're showing it graphically here. Now this is the simplest case whenever we have a flat line. Let's do something a little more interesting. All right, let's go down here. Let me see how many graphs I need to draw, because I need to draw quite a few of them. I think I've got plenty of room. So let's go over here to the other side of the board over here. Let's draw something a little bit more interesting. Let's draw a graph that is not flat, right? Now you gotta forgive me a little bit because I'm freehanding these graphs, right? But I think you can get the big picture here. So let's say, here's 1 tick mark, 2 tick marks, 1 tick mark, 2 tick marks. This is axis is always the time axis in seconds, and this is the distance axis in meters, right? So meters on the top and seconds horizontal right here. And this is -1, -2, -1, -2 like this. I guess I can extend this down a little bit. So let me try to label them. This is -1, -2, this is 1, this is 2, this is 1, this is 2, this is -1, this is -2. So we have the things labeled here. So what I want to do is draw something a little more interesting than that. So what I had over here a minute ago. So what I'm going to do is draw and of course I have this backwards here, sorry about that. This -1 and that's -2 like this, right? So what I want to do is draw 1 point, and we'll put a -3 here as well. We'll put a 3 over here as well, just so we have something different. So I want to put a dot right here, and I want to put a dot right here. And it's never going to be great, okay? So you're going to have to like forgive me a little bit, but I'm going to try to draw a line that goes through those points like this. So it goes through that one and through that one, something like this. It's supposed to be a straight line, right? And through what 2 points? I'll go ahead and put them back on here and make them nice and big. This point here and this point here. So you see, what we have now is a position time graph that's not flat, but it is a straight line, even though my line's a little wiggly, okay? Forgive me. It's a straight line. So if we just said over here that the slope of this line was equal to the velocity, of course in this case it was 0, then the slope of this line should also be the average velocity between these 2 points, right? I'm only looking between 2 points in time. We're not talking about instantaneous velocity, we're talking about the average between 2 points in time and 2 points in space, of course. So, and remember from algebra or calculus, when you have a line slanted up like this, the slope is positive. So we expect the velocity to be a positive number in this case, right? And if we were to have a line that slants the other way, the slope is negative, we would expect the average velocity to be negative in that case. And I'm going to show you that in just a second. But just get the big picture and get the juices flowing here, okay? So let's calculate this and let's see what the slope actually is. So this is a straight line, and before we calculate anything, it's a straight line. So I'll put a straight line here, right? Because the position time graph is a straight line. This means that it's a constant velocity. Now this was a straight line as well, and it was also a constant velocity. The velocity was 0. The velocity between these 2 points was 0. The velocity between these 2 points was 0. The velocity between any 2 points on this line was 0. What I'm saying is that anytime you have a position graph with a straight line, the average velocity between any 2 points on the line will always be the same thing. It'll be a constant. And you can see that it's a constant, right? Because if you look between, for instance, this is the time direction. This is the distance along the x-axis that it goes, right? Between this, let's call it 2 seconds here. 2 seconds in time, between here and here. How far did the thing move? It moved from -1 up to crossing exactly at 0. It should be right on top of 0. So basically, in this span of 2 seconds, it moved 1 meter this way. And in this span of 2 seconds, it also moved a meter. And in this span of 2 seconds, it would move another meter up here. So every 2 seconds, it moves the same exact distance, always, for all time. And that means, since velocity is distance over time, no matter what 2 points you pick, you're always going to cover the same. It's going to be the same meters per second. And that's what you always see. When you have a straight line that's at some angle, the fact that it's a straight line tells you that it's always a constant velocity, and the slope of that line tells you how fast it is, or what the magnitude of that velocity is, how much velocity you have. And no matter where you calculate it, you're going to get the same thing. So let's go ahead and do that. Let's calculate it 2 different ways, right? Let's calculate it first by looking at the velocity between these 2 points that I have on the board right here. So the slope is x, I shouldn't say the slope. Let me go ahead and do it right. We'll say that even though we know it's the slope, it's the average velocity. That's what we're calculating. x2 minus x1 over time 2 minus time 1. Now notice that this is, over here, time is 2 seconds before I've started my clock. Time over here is 2 seconds after I've started my clock. Don't get scared off by negative time. It just means that's how many seconds before I started my experiment, or before the 0 point of my experiment. All right, so what is the x position in the final state? Because notice time is going this way. So you're traveling kind of this way. And so here is the final state. The x position right here, the position is 1 meter, positive 1 meter to the right. So it's 1 meter minus the initial position. The initial position is here, and here my initial position is negative 1 meters, like this. So you have 1, because you got to kind of project it onto this axis. Your final position was 1 meter to the right, and your initial position was 1 meter to the left. So we subtract final minus initial. The final time was at 2 seconds, and the initial time was at negative 2 seconds. So we have final position minus initial position. We have final time minus the initial time. What do we get? We get 1 plus 1 on the top, and we get 2 plus 2 on the bottom, and we get 2/4, right? Which is what? 1/2. And what did we calculate? The top is the number of meters I traveled between these 2 points, going from here to here. And on the bottom, it's the number of seconds. So it's meters on top and seconds on the bottom. So the average velocity is 1/2, positive 1/2 meters per second. Now we said in the last lesson, we introduced the concept of a vector. We said that vectors are very special in physics, and they're very important because they have 2 parts. A vector is an object that has a magnitude, which is the number, and it also has some sort of direction component. So for this, I'm telling you ahead of time that velocity is a vector. In the last lesson, we also learned that displacement was a vector. So velocity is also a vector. So is acceleration, that's a vector. So is force, that's a vector. There's lots of vectors. We're going to learn about them forever, okay? Velocity is a vector. Why? Because the 1/2 tells me how fast I'm moving, that's the magnitude. But there is a sign component here. The implied positive sign that's here tells me that I'm moving in the positive x direction. Remember, we're looking on our side here, so this is a number line. This is the positive x direction. So it's telling me I'm going at a speed of 1/2 meters per second in the positive direction. Starting from here, I'm traveling this way to the positive direction. If there were a negative sign here, which we'll do in a minute, it would mean that I was going toward the negative part of the number line. So if you want to think of the number lines that we had before, where I just kind of said here was 0, this is the x direction, what it's basically telling me is that I'm traveling this way at a velocity of 1/2 meter per second, 1/2 meter per second. Positive means I'm traveling to the right, which is in the positive x direction on my graph here. Now we've established that between these 2 points, the average velocity is 1/2 meter per second squared. Let's see if it makes sense. Because we just said that the slope of anything is the rise over the run, and what we basically are calculating is how far we're going up, rise, and the run over here. So this right here, this 1/2 should be a rise of 1 and a run of 2. So if we start right here, rise up 1, run number 2 spots over. And then we go up, rise, up 1, and then over 2 right here. So rise and then over, rise and then over. Up 1 over 2, up 1 over 2. And you can see that the slope of this graph is 1/2 from looking at the graph, and the velocity we calculated is also 1/2. Once again, the slope of the line on the position graph is equal to the velocity between the 2 points. Now, because it's a straight line and the slope of the line never changes, then if we calculate the average velocity between any 2 points on this line, on this graph, we should get the same velocity, 1/2 meter per second, because it's never your position is changing, but no matter where you are, you're going the same distance in the same amount of time, no matter where you are on this thing. So let's go ahead and calculate it someplace else. Let's say between t is equal to 0 and t is equal to 1. I want to do it between time is equal to 0 and time is equal to 2 seconds, right? So let's see what we get. The velocity, the average velocity, is, of course, x2 minus x1. That's the distance traveled, t2 minus t1. All right, so where is my final position? If I'm only looking between 0 and 2 seconds, my final position is up here at 1 meter away, positive 1 meter away. But my initial position at time 0 is at the origin, 0. So final position over here is at 1 meter. Initial position at time 0 is 0 meters. All right? Now the final time is 2 seconds and the initial time is 1 second because that's my window here. So I should say my final time is 2 seconds and my initial time is 0 seconds. So once again, final position at 2 seconds is 1 meter. And the initial position is 0. My final time is 2 seconds. My initial time is, again, 0 seconds. So what do I get here? Between here, I have 1/2, and it's meters per second. So you can see that when I calculate the average velocity between these 2 points, I get 1/2 meter per second. And when I calculate the same exact thing between these 2 points in time, between 1 and 2 seconds, I get the same thing. And that's because what we're really calculating is the slope of this line. The slope of the line never changes no matter what points you pick. So when a line on a position graph is constant, like a line that never changes its slope, the slope of the line tells you basically the speed. The sign that you get tells you the direction, but the average velocity you calculate is always going to be the same. All right, so we have rise over run like this. All right, so the magnitude of the velocity is 1/2. The plus sign that is here means it moves to the right. So moves. And when I say moves to the right, really what I'm trying to say is it moves in the plus x direction. In other words, it's moving from smaller values of x to bigger values of x. That's the direction it's moving, or this way, if you want to think of it, turn it on your side like this. If you were to get a negative sign for the velocity, it would just be going in the opposite direction. All right, so we have two situations. We have a velocity of 0, that's a slope of 0, which is a horizontal line here. We have a very small kind of velocity. Here's a fraction, 1/2 meters per second, and this is what it looks like. So what do you think is going to happen if we make this thing a little bit steeper, if we make this graph a little bit steeper? Well, the slope of the line will be steeper, so the velocity will be steeper. So we're not going to calculate this one, but what would happen if we had a situation where the position time graph, this is time in seconds, and this is x in meters. I'm not even going to put any numbers or anything like that. I'll just put some tick marks, same as before, just like we did before. I'll just put some tick marks here. I'm not going to label them. I'm not going to calculate this one or whatever. But what if it was a much steeper situation, something like this? Is the velocity, the average velocity between any 2 points on this line, going to be higher or lower? Well, this is a constant velocity because it's a line, right? And this is a higher velocity. Higher than what? Higher than this one. This is a lower velocity. Whoops, if I can spell velocity right. And why do we know this? Well, first of all, I've kind of proven to you that the slope of this line is the velocity. Here we have a lower, a shallower line, lower slope, so we have a 1/2, and that's a lower velocity, and because the slope is lower. So if we have a situation where the position time graph is very, very steep like that, that's going to be a higher slope, which means a higher velocity. Now you can also think through it a little bit. Look what's happening in the first second. This is time, right? In the first second, this thing is shot up already 1, 2, 3 meters. That was kind of an accident to make it nice like this. In the first second, it went up 3 meters, right? From down here, if you want to look at this second, it went up 1, 2, 3 meters as well. So it appears, even though I kind of just accidentally drew it this way, the velocity here, the average velocity is 3 meters per second. Why? Because here the rise of this line is 1, 2, 3 meters, and it did that in about 1 second. I'm calling it exactly 1 second. So 3 distance units traveled 1 second of time. 3 over 1 is 3 meters per second. Again, the plus sign that's here means it moves in the positive x direction. So the sign carries the direction, the number carries the magnitude. So all I'm trying to do really at this point is to connect the idea that the slope of a line on a position graph is equal to the velocity. It's extremely important. We learn it in calculus. We call it the derivative in calculus, and we consider more complex situations in calculus, but that is what we're doing here, okay? Now, here we've had a slope of 0, we've had a positive slope, and we've had a positive slope, which is a larger positive slope. What would happen if we actually had the line tilt the other way to make a negative slope? Let's go calculate one of those situations and see if we can figure out what we would have. So let's go over here and draw another situation. Again, freehand, so I'm not perfect, so don't shoot me, right? Because I cannot draw them perfect like this. But I can do a pretty good job. So let's call it, here's 1 tick, 2 ticks, 3 ticks, 1 tick, 2 tick, 3 tick, 1, 2, 3, 1, 2, 3. I'm not going to put the numbers. I know that you all know these are positive and these over here are negative. So I want to draw a line that goes between this point right here and this point right here. So I'm going to do my best. It's not going to be perfect, so please don't get too mad at me, but it goes through this line. Ugh, that is terrible. That is terrible because it should go through the origin. It just erased the whole thing and start over. So like this, it should go through the origin. I'll kind of connect this back here like this. Okay, so it's something like this. It goes through the origin and then through this like that. That's a lot better. Still not great, but it's a lot better. So there's a point there and there's a point right there. So notice, first of all, that the slope of this line is we know it's going to be negative if we were to think about algebra, right? Because it's tilted the other way. So that would tell us that the average velocity between any 2 points on this line will be negative, and no matter what 2 points we pick, it'll always be the same negative slope, so the same negative average velocity. What does a negative average velocity mean? Let's calculate it. So the velocity in this case, the average velocity in this case, is the same thing as always. It's x2 minus x1, the final minus initial, and then t2 minus t1, final minus initial. Now, time is marching along this direction. So this is the final, so this is the end, and this is the start, right? Because time is going this way, and so what's happening is you're starting here, because this is up here, and you're traveling down the x direction, and you're ending right here. So what is the final position? This is -2. Because this is the final position at -2, a position of -2. What is the initial position? That's way over here at x is equal to +3. So +3, so -3, like this. So the final position was here, the initial position was here, the final position was -2. The initial position here was +3, so -2 minus 3. Now the final time is 2 seconds. This is 2 seconds. And the initial time is way over here. This is -3 seconds right here. So all we are doing is we're looking at final minus initial for the x and for the t. So what do we get here? -2 minus 3 is -5. Here we get 2 plus 3. That'll be a +5. And what we get when we divide is -1 meter per second. Notice that we did get a negative value. And this is the same thing as you can think of it as -1 over 1 in terms of rise over run. Right, if you want to think of algebra, right? So that means the slope of this line, you can think of it as rising down, because rising down means negative, and running over to the right 1. So rise down 1 over 1, down 1 over 1, down 1 over 1, down 1 over 1. And that is a slope of -1 meters per second. But what does it physically mean to have a negative average velocity between these 2 points in time? What it means is that whereas before, the positive sign means I move in the positive x direction, the negative sign here means I move, if I can do move, in the negative x direction, or towards the negative x direction. What it means is, notice I start here, and I end here, and I'm traveling this way down the x-axis. I'm traveling towards values of -x. I'm traveling towards smaller and smaller and smaller values of x. It's telling me I'm going down in x. or if you tilt your head sideways, to the left. Whereas before, it was telling me that I was going in the positive x direction with a positive number. Here it's telling me I'm going down in the negative x direction. So velocity, again, average velocity, it carries information related to how fast you're going, that's the number, and the sign conveys the direction. That's what makes velocity a vector. There is a direction component and there is a number component. And vectors are so important. We're not going to get away from them. So I'm going to emphasize that over and over again as much as I need to. If you want to turn your head sideways again, like we were doing in the last lesson on a number line, here, instead of looking like this, then basically what we're saying is that we're traveling this way at 1 meter per second. I'll put the negative sign. That just means we're going towards smaller and smaller values of x, right? All right, so we calculated -1 meter per second using these 2 points. I would encourage you, if you pick any other 2 points, like if you choose these 2 points, or these 2 points, or 2 other points that I haven't even put dots on, you will always find the velocity to be -1, because what -1 meters per second means is that I go down 1 meter for every second. And you can see that I'm doing that no matter where I'm at on this line, right? And the reason that the velocity is the same everywhere is because it's a line and the slope of a line never changes. So now what we have to do is open our horizons a little bit and talk about what happens when the position does not form a line like that. Like what happens? In this case, we had a flat line of 0, then we had a shallow line, then we had a very steep line, then we had a negative line. And we know that motion is more complicated than that. In all of these cases, the velocity was constant. But what happens when the velocity, when the speed is changing? What does that look like on a graph, right? So let's go and take a look at that. And this is probably the most important graph in the whole lesson, so I really want you to pay attention to this one. Here we have the y-axis, and then here we have the x-axis like this. Same thing, t in seconds, and this is x in meters. All right. Now what I will do, I will try to draw these because I do want to make sure I get them right. And I'm probably going to need to extend this down a little bit. So here we have 1, then 2, then 3, and then 1, -1, -2, -3, -4, -5. So I'll go 1, 2, 3. I'll call this 1, 2, 3, 4, 5. So where do I put these? I guess I'll do it 1, 2, 3, 4, and 5. I don't think I'm going to need any here, but of course I have tick marks over here. I can do -1, -2, -3, -4, -5 in terms of the position. All right, so what I want to do is I want to take a look at the places. Here is a dot I'm going to put right here. And then over here, I'm going to put a dot right here. All right, but instead of drawing a line between them, what actually happens is this thing is like a bunny rabbit or something. It's like a little unpredictable. It jumps, it goes really, really fast, and then it goes really slow, or it changes its speed, right? So let's see what that would look like. If we did something like that, we could have a situation like this, where it maybe starts here, it goes up very, very, very fast, then it bends over, and it kind of goes horizontal like this. Or actually, I think I like a better situation. The dot was right here. I think I want to bend it over a little bit sooner, and it goes something like this, right? Now this is obviously not a straight line. But notice if you kind of break it up into segments, you can kind of see what's going on. If you kind of look in this segment right here, we have a kind of a line. It looks very much like a line with a positive slope. And also it's extremely steep. It looks kind of like this one down here. And we know that this was a very high velocity. So this is a high velocity, kind of in this region right here. But then it bends over like this. Here you have kind of like intermediate speed, or I should say slower. And then here, once it gets way over here, this is the slowest. Why? What am I doing here? Because I'm just kind of mentally looking at the slope. Now, of course, it's always changing, but you could imagine that if you kind of put your pencil here, this thing is a lot less steep than this. This is the most steep, this is middle steep, and this is the shallowest of them all. And if you just kind of picture the slope of these little line segments that are here, then you can visualize this is very high velocity, this is middle velocity, and this is the slowest velocity. So right here, like in 1 second between here and here, you travel a great distance. That's very, very high velocity. But between here and here, you travel, between 2 and 3 seconds, you travel not as far. But then between maybe 4 and 5 seconds, you travel very, very little at all because your distance is, of course, the vertical aspect of it right here. So that's why this is the slowest, because you're in 1 second, you're not traveling as far as you are down here. All right, so what's going to happen if I want to find the velocity of this? Well, later on, we're going to talk about instantaneous velocity. We're going to talk about what's the velocity right at this point. What's the velocity right at this point? What's the velocity right over here at this point? That would be the instantaneous velocity. We're going to have to put that on the back burner for another lesson. But what if I just wanted to find the average velocity between the two red dots that I have drawn on this picture? Between this dot and this dot, what would the average velocity look like between those two dots, for instance? So what I could do is I could draw a line that kind of cuts through these, and I'm probably going to mess it up, so I'll try not to desperately. I'll kind of go like this, and I'll try to draw it like this. So there is an arrowhead, and there's an arrowhead. So notice what I've done. Let me take this arrow out because that's confusing, and I'll say high velocity. I'll kind of put a little, I'll put the little like this. So it's a high velocity aspect of it. But you can see that if I want to find the average velocity between 2 points, any 2 points, on a position time graph, even when it's a curve and it's not a line at all, what I do is I put my 2 dots on the graph and I draw a line between them. And essentially, the average velocity between those 2 points will be, can you guess, the slope of this dotted line that connects these two things. Now, you can see that even once I calculate the slope, I am ignoring all of the ideas, everything that's happening in here. I'm kind of ignoring them. I'm only looking at only the end points, because we know it's traveling faster here, and we know it's traveling slower here. But between these 2 points, we're ignoring all of that, and we're only considering the endpoints, and so we're calculating an average, which is exactly what it sounds like. It's an average of all of the changing velocity that's happening between those points. You're basically ignoring the speeding up and the slowing down, and you're picking one number out that represents the average distance per time. So let's calculate what that is, right? The average velocity between these 2 points right here is the same thing as always, x2 minus x1 over t2 minus t1, right? Now, time is flowing this way. Time is increasing. So this is the final position, and this is the initial position. So I'll put final, and I'll put start here. I'll put st for start, right? So what is the position? The position over here, because this is time, right? The position is 2 meters, positive 2 meters. And the initial position is here. The initial position over here is negative 4 meters. So it's negative 4. So it's 2 minus the negative 4, okay? Now, again, going back to the final, for the time, this time marking is at 4 seconds, positive 4 seconds. And this initial position, or over here, is at a time of 1 second. So it's 1 second. So it's final minus initial, final minus initial. All right, so what we get is this is going to be a plus sign, so you're going to get a 6 on the top. Here you're going to get a 3 on the bottom. And so the velocity, average velocity, is 2. 2 what? 2 meters per second. This is the average velocity. Average velocity over this interval of time of this motion between these 2 dots. And basically we know that the actual speed was faster in this region and slower in this region, but as an aggregate, it covered a distance of 2 meters every second. So, and you can see that in this second right here, in this second between 1 and 2 seconds, it went up 2 meters, right? And then in this second right here, it went up 2 and then again over 1, and then up 2 and then over 1, because 2 meters per second is like going up 2 and over 1, rise over run. All right? So again, the dotted line here is the slope of the line between those 2 points. That gives us the average velocity. Now this is a segue. I'm going to draw lots more pictures later. Right now, we're only interested in the average. On average, that's what that's the distance it traveled, 2 meters every second. We know it traveled faster here. We know it traveled slower here. But as an average, 2 meters per second between the endpoints, okay? But what we're going to do later is we're going to talk about the instantaneous velocity. And what we'll do is we'll start to bring these 2 points closer together. So we're always finding the slope of the line connecting. Like imagine if I pull this dot over here, and then I would find the average velocity there between these 2 points. And what if I pulled it here? Then I would find the average velocity connecting those points. What if I put these 2 dots pretty much almost on top of each other? Then I would be finding the slope of the line barely touching the graph, and the slope of the line, we call it tangent to the graph. That is the instantaneous velocity at a single point in time, which we call in calculus, we call that the derivative. of the position. We say the derivative of the position is equal to the velocity. And the idea of a derivative is we just draw a line tangent to the graph, barely touching the graph, and find the slope of that line, right? And so that is what we're going to get to a little bit later. Now, there's one more thing that I want to talk about before I close the lesson up, because we're almost done. And this is the idea of average speed. Because people think average speed and average velocity are the same thing. All right, notice that what we did here is when we calculated the average velocity, we only considered the endpoints, right? We didn't consider really anything that happened. It was only where is it, and how long did it take, and that's it. The endpoints, that's all that matters. But remember, just like there's a difference between displacement and distance, right? There can be a difference in some cases between average velocity and average speed. The average speed we're going to write down as S for speed, and we're going to put an average bar on there. And this is the total distance divided by the time, delta t. You might say, well, what is that? You said it's distance over time, and you've been telling me the whole time it's distance over time here as well. What's the difference? Well, imagine a situation where, remember, this is only one-dimensional motion. Let's imagine a situation where we have, this is now, I'm going to get rid of the XY graph here. I'm just going to talk about a number line here. And here is the position of something in meters. Let's say that you start, I don't know, you start over here. This could be like 1, this could be 2, this could be -1, -2. Let's say that you start right here. I'm going to put a dot right here. But let's say, instead of just, this is the starting place, and then you end up over here somewhere, but instead of going straight from here to here, what you actually do is you travel back 1 meter, or you go this way, then you go back to your starting point. Then you go back to 0, then you go back 1 more, and then finally you end up over here. So you see what happens? The starting point is at 2 meters to the right. The ending point is at 2 meters to the left. So the speed would take into account the total distance of all the zigzags if you backtrack on yourself. So this is like 1 meter, 2 meters, 3 meters, 4 meters, 5 meters, 6 meters, 7 meters. That's like 8 meters, right? Let's do it again. 1, 2, 3, 4, 5, 6, 7, 8. That's like 8 meters. So however many seconds it took, you would when you calculate the speed, you would be counting all of the backtracking that you're doing on yourself, and it's 8 meters, right? And however long it took, that would be the speed, because that's how far you went over that time. But the velocity is only going to consider the endpoints. You start 2 meters away, you end 2 meters to the left, so you really traveled only a net distance of 4 meters. That's 1, 2, 3, 4. That's just based on the endpoints, 4 meters in the same amount of time. So you see how the speed and the velocity can be totally different, but usually it's only a difference if you backtrack on yourself, right? Usually if you're just going from here to here, the speed and the velocity are the same because you're going in one direction. But if you ever go and then turn around and come back, and then go and then turn around and come back, and then go and then turn around and come back, well, then the speed takes into account all of the distance and all of the time, but the velocity only takes into account the endpoints. So the velocity is going to give you, in general, a different number than the speed in some cases, and we'll do some problems based on that. All right, so we have conquered the idea of average speed and average velocity, and it's so important. I want to do a little summary at the end to make sure we're all on the same page, because this stuff is very important. We're going to get into more of it later. We said the idea of average velocity basically takes a look at figure out how far you traveled based only on the endpoints, though. Final position minus initial position, and then the difference in the time, and you get a unit of meters per second, right? We can graph the position vertically and the time dimension horizontally. If you have a horizontal line, then what you end up calculating is a velocity of 0 meters a second, because at every point in time you really haven't changed your position. You're always at -1. And notice the slope of any horizontal line is 0, so we made the connection and said that the average velocity you get between any 2 points on this line is always 0, which is the slope of any horizontal line. And then we said, what happens if you end up with a position time graph that's slanted? Well, what happens is, if you calculate it, the velocity between these 2 points, at time is equal to 2 and time is equal to -2, then we get a velocity of 1/2 meters per second. But if we calculate the velocity based on two different points on exactly the same line, we again get the same exact thing. So anytime we have a position graph that is a straight line, we know it's a constant velocity that never changes. And no matter what 2 points we pick, we always get the same velocity. And the slope is a positive number, a small positive number, because it's not very steep, because the slope of the position curve is equal to the velocity, because slope is rise over run. And so what we calculated here is the rise, the delta x going up, and the run, delta t, going over. So slope and velocity are interconnected to one another, okay? Then we said, what if the line gets steeper? If we calculate it even steeper, we're going to get a bigger number because you're going farther in the same amount of time. So the steeper the line, the steeper the slope, the higher average velocity between any 2 points on a line, and always lines like this give us the same constant velocity. The velocity is not changing, okay? Now, we say, what happens if you have a velocity position line that is slanted the other direction? We said, well, it should have a negative slope. Let's see. When we calculate its velocity based on its ending position minus its starting position like this, we get a negative number, -1 meters per second. And this is like -1 rise over run. And we convinced ourselves that exactly the slope corresponds with going down 1 unit for every second like this. And we said that every one of these calculations gives us a number and a sign. The number tells us how fast we're moving in terms of meters per second on average between the points. And the sign tells us what direction. We're moving now in the negative x direction down here. In the past, when we had positive average velocity, we were moving towards the positive x direction. And then finally, we said, well, what happens if the position graph is not a line at all? What if it's some weird curve like this? Well, if you want to find the average velocity between 2 points, what you do is you put the points on the graph, and you are going to calculate the same thing here. But what you're doing is you're finding the slope of the line between the 2 points. So what you're doing there, if you put 2 points on any curve, no matter what shape it has, if you find the average velocity between these 2 points, you're taking delta x over delta t, which is the slope of the line that connects those 2 points. So this slope of this line worked out to be exactly 2, which we can verify, up 2 over 1, up 2 over 1, and so on. And of course, it's the same thing. The number tells us how fast we're moving. The sign tells us we're moving in the positive x direction. So it has a magnitude and a direction. And later on, I said, as we bring these 2 points closer together, we'll do this in future lessons, we're going to calculate the instantaneous velocity at a single point by bringing these points together. And what you're doing is you're finding the slope of the line between those 2 points as those points get right on top of each other. And in the case of instantaneous velocity, it ends up being the slope of the line tangent to the position curve, which in calculus we call the derivative. That comes in a later lesson. It's kind of a preview. And then the last thing we said is the average speed is sort of the same thing. It's distance divided by time, but it's the total distance. Even if you backtrack on yourself, you count all of the distance and all of the time. And so if you ever backtrack, because the velocity only takes into account the endpoints and the speed takes into account every movement of the distance, then you can have an average speed and an average velocity different. But in general, it's only going to happen if you take a different path. You know, if you backtrack on yourself or you take a different path. So, a lot of stuff we did here. Believe me, I would not waste my time talking about it for such a long time if it wasn't really important, because we're going to solve some problems in the next lesson. Then we're going to talk about motion in 2 and 3 dimensions. And when you understand this stuff really well, like I'm hoping to have done here with you, then the future stuff just becomes much easier to comprehend. If you don't know this stuff, then you can't understand 2 dimensions or 3 dimensions because you don't know this. So I'd like you to watch this a couple of times if you need to. Follow me on to the next lesson. We'll continue to solve more problems to give more practice with average velocity and average speed.